Question number 4. A laminar boundary layer velocity profile is given by function of eta equal 2 eta minus 2 eta cubed plus eta by the power of 4. So here we assume that function of eta is equal to u over u and eta is equal to y over delta. So the question asks you to find what is the value of delta star over delta and theta over delta. So this is not a new velocity profile. It is actually the same velocity profile that we already solved in tutorial number 1. So if you see in question number 1, we use velocity profile of u over u here. So it can be simplified as this one by simplified y over delta is equal to eta. So it will become 2 eta minus 2 eta cubed plus eta by the power of 4. So to solve this problem, you have two methods. One, you just replace the value of eta here by the value of y and delta, and you could solve it by using the previous method. But in this tutorial, I would like to show you another method to solve this problem by simplifying the value of y of delta with eta. So this is the equation for displacement thickness. Delta star equal integration of from 0 to delta of 1 minus u over u dy. We need to modify a little bit here to derive a new equation to be used with eta velocity profile. So from the previous statement, we know that eta is equal y over delta. We could write that d eta is equal to dy over delta, and then we could write that dy is actually equal to delta times d eta. So what we need to do is we substitute all this value into this equation. So means that the dy here is replaced by delta and d eta, as you could see here. So the value of u over u is replaced by function of eta, f eta. Then the value of limits need to be changed too, because here we are integrate to d eta, so means the value of 0 to delta is invalid. So the limit need to be changed. So it can be changed by looking to this equation. So means that if y equal to 0, because previously it is integrate to dy. So if y equal to 0, we substitute here. So we find that the eta is equal to 0. Then if y equal to delta, substitute it here. So we have delta over delta. So eta is equal to 1. So this is the limit that we need to change from 0 to delta to become 0 to 1. So finally, the equation for displacement thickness to be used in the function of eta is integration of 0 to 1, 1 minus function of eta, delta times d eta. Please remember this if you want to use or you want to solve problem of velocity profile that having eta. So for our notes, so this is the displacement thickness equation, delta star over delta for function of eta, and this is the equation for momentum thickness for function of eta. So it looks like similar with the previous equation, so I hope you don't confuse compared to the previous equation. So the major difference is the limit need to be changed. Instead of 0 to delta, you need to use 0 to 1 as your limit now. So let's say this is our velocity profile, 2 eta minus 2 eta cube plus eta by the power of 4. So we need to determine what is the value of delta star over delta. So we substitute this equation with the function of eta that given in the question. So we substitute it here. Please be careful because the minus here will change the minus of this one into plus sign. We complete the integral process and the limit is 0 to 1, so we get the value of delta star over delta is equal 3 over 10. So the answer here must be same with our total real 1 equation number 1. So the advantage of this integral method or this equation is we could save time to do the integral process compared to the y over delta method. And then if you do the theta over delta, do the same things, substitute the value of f eta here with the function of this one, complete the integral process, you could find that theta over delta is equal to 37 over 315. Please be careful please try this at home. Please subscribe this channel, C23 Classroom channel. Thank you for watching.